Space is vast. It's filled with incredible objects. Some of the most fascinating are black holes. Imagine a place with gravity so strong not even light can escape. That's a black hole. They're like cosmic vacuum cleaners, but not quite. Don't worry, we'll explain. Black holes are mysterious and awe-inspiring. Let's dive in and explore these cosmic wonders. Everything in the universe has gravity. It's the force that pulls things together. The more massive an object, the stronger its gravity. Black holes are incredibly massive for their size. This means their gravity is extremely strong, so strong in fact, that nothing can escape their pull, not even light.
Black holes aren't really holes. They're some of the most fascinating and mysterious objects in the universe. Despite their name, they are not empty voids, but rather regions of space where gravity is so strong that nothing, not even light, can escape from them. This makes them invisible to the naked eye, but their presence can be inferred by the effects they have on nearby stars and gas. They're objects packed with immense amounts of matter in a tiny space. Imagine taking a star, which is millions of times larger than Earth, and compressing it into a sphere just a few kilometers across. This incredible density gives black holes their powerful gravitational pull. The process of a star collapsing into a black hole is a dramatic and violent event, often resulting in a supernova explosion that can outshine an entire galaxy for a short period. Think of a star squashed down to a single point. This point, known as the singularity, is where all the mass of the black hole is concentrated. The singularity is a place where our current understanding of physics breaks down as the laws of gravity and quantum mechanics clash. It's a region of infinite density and zero volume, a concept that is difficult to grasp, but crucial to the nature of black holes. This point is called the singularity. The singularity is surrounded by the event horizon, which is the boundary beyond which nothing can escape the black hole's gravitational pull. The event horizon is often referred to as the point of no return, because once an object crosses this boundary, it is inevitably drawn into the singularity. It's where gravity and density become infinite. The intense gravitational field near the singularity warps space and time to such an extent that time itself slows down relative to an outside observer. This phenomenon, predicted by Einstein's theory of general relativity, means that an object falling into a black hole would appear to slow down and freeze at the event horizon from the perspective of an outside observer. Surrounding the singularity is the event horizon. The event horizon is not a physical surface, but rather an imaginary boundary. It marks the limit where the escape velocity equals the speed of light. Anything that crosses this boundary, including light, cannot escape the black hole's gravitational grip. This is the point of no return. The event horizon is a critical feature of black holes, defining their size and shape. It is often depicted as a dark sphere surrounded by a glowing ring of light, which is actually the light from nearby stars, and gas being bent and magnified by the black hole's gravity. Once you cross it, there's no going back, not even for light. The gravitational pull is so strong that it warps the fabric of space-time, creating a one-way path to the singularity. This means that any information or matter that falls into a black hole is lost to the outside universe, making black holes some of the most enigmatic objects in existence. Further out, you might find a swirling disk of gas and dust called an accretion disk. This disk forms as matter from a nearby star or interstellar medium is drawn towards the black hole. The material in the accretion disk spirals inward, heating up due to friction and releasing vast amounts of energy in the form of X-rays and other radiation. It's heated by friction as it spirals into the black hole. The intense heat and radiation from the accretion disk can outshine the entire host galaxy, making black holes some of the brightest objects in the universe despite their name. The study of accretion disks provides valuable insights into the behavior of matter under extreme conditions and the growth of black holes over time.
Stars are giant balls of burning gas. They live for millions or even billions of years, but even stars don't live forever. When massive stars die, they can collapse under their own gravity. This collapse creates a stellar mass black hole. These black holes are several times the mass of our sun but squeezed into a space smaller than a city.
Section 5. Supermassive giants, the hearts of galaxies. If stellar mass black holes are big, supermassive ones are truly mind-boggling. These behemoths lurk at the centers of galaxies, including our own Milky Way. They can be millions or even billions of times the mass of our sun. How do they form? That's still a mystery, but they likely grow by consuming stars and gas clouds over billions of years.
Section 6. Elusive middleweights. The hunt for intermediate mass black holes. Astronomers have found evidence for a third type of black hole, intermediate mass black holes. These are the missing link between stellar mass and supermassive black holes. They're thought to be hundreds to thousands of times the mass of our sun. Finding them is tricky, but their unique signatures are starting to emerge from dense star clusters and dwarf galaxies.
Section 7. Echoes from the Big Bang primordial black holes. Imagine black holes forming right after the Big Bang. These are called primordial black holes. They could be incredibly tiny or surprisingly massive. Detecting them is a huge challenge. If found, they could help us understand the early universe and the nature of dark matter.
Section 8. Peering into the darkness, detecting the unseeable. The universe is vast and filled with mysteries, many of which are hidden from our direct view. Among these enigmatic phenomena are black holes, regions of space where gravity is so strong that nothing, not even light, can escape. If black holes are invisible, how do we find them? This question has puzzled scientists for decades. The answer lies in the indirect evidence we can gather from their interactions with the surrounding environment. We look for their effects on their surroundings. Black holes, despite being invisible, exert a powerful gravitational pull on nearby matter. This gravitational influence can cause nearby gas and dust to swirl around the black hole, creating a distinctive pattern that we can observe. When matter falls into a black hole, it heats up and emits X-rays. This process, known as accretion, generates high-energy radiation that can be detected by X-ray telescopes. These X-rays provide a crucial clue to the presence of a black hole. We can detect these X-rays with special telescopes. Instruments like the Chandra X-ray Observatory are designed to capture these high-energy emissions, allowing scientists to pinpoint the locations of black holes across the cosmos. We can also observe the orbits of stars around unseen objects. By studying the motion of stars, we can infer the presence of a massive, invisible object exerting a gravitational force. If the object is massive and invisible, it's likely a black hole. These observations, combined with theoretical models, help us understand the nature of these fascinating cosmic entities. Detecting the unseeable requires a blend of advanced technology, keen observation, and a deep understanding of the laws of physics.
Section 9. Spaghettification and other cosmic horrors. What would happen if you fell into a black hole? Let's just say it wouldn't be pretty. The immense gravity would stretch you out like spaghetti, a process called, appropriately, spaghettification. Time would also get weird. It would slow down for you compared to someone watching from afar. Black holes are fascinating, but you wouldn't want to get too close.
Section 10. Black holes, not so black after all. Black holes are famous for their darkness. They are regions in space where the gravitational pull is so strong that not even light can escape from them. But they might not be completely black. Contrary to their name, black holes can emit a form of radiation. In the 1970s, the renowned physicist Stephen Hawking proposed a groundbreaking theory. He suggested that black holes could slowly emit radiation, a phenomenon now known as Hawking radiation. This radiation, called Hawking radiation, is incredibly faint and difficult to detect. It arises due to quantum effects near the event horizon of the black hole. If it exists, it means black holes slowly evaporate over time, though this process takes much longer than the current age of the universe. The evaporation process is extremely slow, taking billions of years for a black hole to lose a significant amount of its mass. The concept of Hawking radiation bridges the gap between quantum mechanics and general relativity, two fundamental theories in physics. It suggests that black holes are not entirely isolated from the rest of the universe. According to Hawking's theory, virtual particles are created just outside the event horizon. These particles come in pairs, with one falling into the black hole and the other escaping into space. The particle that escapes carries away a tiny amount of the black hole's energy, leading to a gradual decrease in the black hole's mass. Over an incredibly long period, this process could cause the black hole to shrink and eventually disappear. However, this would take much longer than the current age of the universe, making it a theoretical concept rather than an observable phenomenon. The idea that black holes are not entirely black challenges our understanding of these mysterious objects. It opens up new possibilities for studying the universe and the fundamental laws of physics. As we continue to explore the cosmos, the study of black holes and Hawking radiation remains a fascinating and evolving field, offering insights into the nature of space, time, and the universe itself.
Section 11. Unraveling the cosmos, black holes and the future of astronomy. Black holes are some of the most extreme and mysterious objects in the universe. By studying them, we can learn about gravity, the life and death of stars, and the evolution of galaxies. New telescopes and techniques are constantly being developed, promising even more exciting discoveries about these cosmic wonders in the years to come.